My name is Mohammed Aslam. I am a PhD candidate at Ghent University. The title of the demo paper I am going to present is High Precision Time Synchronization on Wi-Fi based multi-hop network. Let me share the screen with you so you can see the slides of my demo paper. So high precision time synchronization on Wi-Fi based multi-hop network. The first question arises, why do we care about clock synchronization? Because it enables nodes in a distributed network to share same notion of time. And it is very important for a system where the performance highly relies on a clock synchronization accuracy of the network. The example includes audio or video streaming over distributed network, network-based motion controls. Thus, we demoed on how to achieve a better clock synchronization accuracy of our Wi-Fi based multi-hop network. PTP, it is a state-of-the-art clock synchronization protocol introduced in IEEE 1588 standard. It is capable of achieving sub-microsecond accuracy in a local network. The accuracy of the PTP highly relies on timestamping mechanism, which can further categorize into software timestamping and hardware timestamping. The software timestamping is realized on application level or in a driver level. It is easy to realize, it doesn't require any extra hardware. However, it provides poor CS accuracy. On the other hand, hardware timestamping is implemented at or closer to the physical layer. It requires a dedicated hardware for timestamping. It is harder to realize but provide better clock synchronization accuracy. Related work. There are already many Ethernet-based PTP work both in academia and industry. As we know that Ethernet are wide-based. Example includes 1210 controller, 700 series adapter, Marvel Fast Link Q adapter, etc. There are few Wi-Fi vendors which claim they also support PTP. For example, Intel chipset, they support FTM, which is a specific profile of PTP. However, on further exploration, we found that it is designed specifically for ranging application and it doesn't expose timestamping to the upper layer. So as it is, it cannot be used for clock synchronization application. Therefore, to the best of our knowledge, there is no commercial of the shelf Wi-Fi cards which support PTP with hardware timestamping. The demo is realized in the YLab testbed. This picture shows how the testbed looks like. This is the block diagram of our demo setup. On the right, on the left side of the block diagram, there is a TSN capable switch which acts as a grandmaster, and at the top of the grandmaster there is a Linux PC which behaves as a wide node to the TSN switch grandmaster. And the bottom at the bottom of the grandmaster there is an Open Wi-Fi AP. Open Wi-Fi is a open source Wi-Fi implementation on SDR, and it is open to the public and anyone can use it. This is a block diagram of Open Wi-Fi. This shows how the Open Wi-Fi looks like. Anyway, the Open Wi-Fi AP in our implementation act as a boundary clock. The interface of the AP attached to the grandmaster behaves as a slave to the grandmaster, and the interface of AP attached to the wireless network domain act as a master to the wireless network domains. In our specific setup, the wireless network domains consist of two Open Wi-Fi clients. On the right side, we simply replace the Open Wi-Fi with the commercial of the shelf Wi-Fi cards. As we already know that no Wi-Fi cards support hardware timestamping. So therefore, here PTP is running with software timestamping by using PTPD application. On the other hand, the setup which consists of Open Wi-Fi, here PTP with hardware timestamping is running by using Linux PTP application. Okay, the results analysis. We did a fair comparison of our PTP implementation with the hardware timestamp with the PTP implementation or with a software timestamp, as we show two different setup in our demo in the previous slide. So the measurement lasts for 300 seconds and the synchronization offset is measured once per second. The 19th percentile of the absolute synchronization offset on each of the uh, network domains is shown in this table. You can see here we have two different columns. One represent for open Wi-Fi measurements, another one represent for commercial of the shelf Wi-Fi cards. So recently, Wi-Fi Alliance has introduced clock sync certificates that says that the 19th percentile of absolute clock synchronization error should be within 5.5 microsecond of the observed time. And the observed time specified by the Wi-Fi Alliance is 120 microsecond. That's why we use 90th percentile here. Okay, based on the table, we can see that the clock synchronization accuracy of open Wi-Fi based PTP is 10,000 better than by using commercial of the shelf Wi-Fi cards. It is worth noting that we also observed that our implementation is prone to traffic load, but these are the potential factor for our future work. Okay, on top of that, we also have recorded videos for the both setup of our demo. The setup with the which contains open Wi-Fi as a wireless API and client is shown here. If I just run this video and stop it, and the node 1 here represent the wired slave to the grandmaster. Here as SDR1 and SDR2 respectively represent open Wi-Fi client A and client B to the open Wi-Fi AP. And the x-axis in all these four graphs represent the time stamping value, and the y-axis represent the clock synchronization error. Let me run the video. So the time stamping values are being updated after each minute. Here we can change the duration. We can see the these clock synchronization error values for last 1 minute. We can switch to more values. We can go to 5, 10, 20 minutes. In this way, we can also see average, maximum and minimum clock synchronization error values here. So, this is what we observed in in the setup contains the open Wi-Fi. This is the next setup, which contains the COTS Wi-Fi cards as a wireless AP and client. This is the let me run this video. Uh, this has the same behavior here. So here the SDR are replaced with the commercial chips. So these are the commercial Wi-Fi uh, cards. So if I pause this video, this is a AP, this is a client A, this is a client B, this is a wired node. In the similar fashion, this clock synchronization error values are for the last 5 minutes. Um, these again represent the clock synchronization error here as well. So we can also change it. Now it shows last the CS values, clock synchronization values for last 15 minutes. That's all from my side. And uh, thanks. And for any question, you can also reach me via muhammad.aslam@ugand.b.